To introduce our keynote speaker, for me as a database engineer, he's somewhat of a database celebrity. Andy Pavlo is a associate professor at Carnegie Mellon University. He's well known for his work in main memory transactional systems and self-managing databases. He's also very well known for his lectures on databases, many of which are publicly available, including also the vaccination database series with many different database vendors. So it's a privilege to have you give the first keynote of the first Citus Con today, Andy. And the screen is yours.
Awesome. You can hear me? Yes? All right. I'm going to assume you can hear me. So let's do this. OK. All right. So today's talk is about the work we've done at Carnegie Mellon, and since some work we've done in the spin-off startup OtterTune on how to automate and the configuration and optimization of Postgres. So database automation and automated administration is an old topic. It goes back to the 1970s. So I want to talk about the more recent work in the last 5 or 6 years on trying to achieve the holy grail of a completely autonomous, or what we're calling self-driving database system. So the reason why we think this is achievable now, even though it's an old topic, is that people have been, people have been working on this for a long time, but the advancements we've had in the last decade in machine learning and artificial intelligence make this actually achievable today. So this talk is not going to be about the ML algorithms or the methods one would use to automate these things, but rather I want to focus on the engineering aspects of what you need to have in a database system to facilitate, to hook in autonomous components, and talk about in particular what we've seen in trying to automate Postgres. So the first thing I want to define is what is a self-driving database system. So I know Oracle has their own self-driving database story and their marketing stuff. But from an academic standpoint, I want to talk about what my definition is. So what we're claiming as self-driving database system is one that can proactively select and deploy actions that will improve or affect the system's objective function without any human input. So by proactive, I mean we're looking ahead and seeing what's coming down in the workload in the future and making changes to prepare for it accordingly. And the objective function would be something that a human has to tell us if they want the system optimized. You want to minimize latency, minimize cost, improve throughput. Right? You have to tell the system what you actually want to improve, and then it figures out how to do it on its own. And the last one is without any human input. This means that we don't have to go to a human and ask them, hey, is it OK to make this change? Or when should I make this change? Or how should I make this change? All these things we can automate to some degree. And this will allow us to achieve what we call a self-driving database system. So the type of actions that we want to support are the classic DBA or administration tasks. The physical database design would be building indexes, partitioning schemes, doing sharding, and so forth. Knob configuration would be the runtime parameters that you can use to modify that control the runtime behavior of the database system, like log file sizes, shared buffers, and so forth. Query tuning is modifying the query, either SQL itself or the query plan to improve the performance of the system while executing it. And then hardware provisioning would be automatically downscaling or upscaling the size of the database instance that you're running on. So key thing we're pointing out, going back to this important issue of without human input, is that all of the design decisions or all the actions that the system is going to take cannot require any human value judgment. And so again, what I mean by that is if there's a decision that has to be made that has an external cost that the database system can't reason about on its own, then we're not allowed to actually make that change. So the classic example I always like to use is if you're trying to maximize performance and the machine learning models figure out, hey, if I turn off disk writes or turn off fsync to make things run faster, that's great. It's going to do that. It's going to learn to do that very quickly. But now if you crash and lose data, that's an external cost that the algorithm simply can't reason about. So we have to, we don't let the models touch that. So there's a variety of things in Postgres that you can do that could affect the safety, durability, correctness of data, and we have to avoid letting the system touch those things. So now you may say, all right, this self-driving claim or self-driving term, is that just a marketing thing? Are we trying to tack on to sort of the excitement people have around self-driving automobiles, self-driving cars, or is there something more fundamental here than why we actually want to use this term? So I would argue that the answer is we are, at least in our own research, we are heavily inspired by the work people have done on self-driving cars, which a lot of it came out of Carnegie Mellon, and we're actually applying that to databases. So at a high level, the self-driving cars sort of work like this. You have sort of three components, three parts. The first is the perception models that allow the car to see what's around it, see what's up ahead on the road, and plan accordingly, understanding what's going on around in its environment. The next is you have to have these action models that will can predict how the car will perform and its position will change on the road and its velocity and so forth as you start making changes to or inputting actions in terms of driving the car. So the basic idea is that you would have something that keeps track of like what's the rotation of my wheels, what happens when I turn the steering wheel this way versus that way, apply the brake or accelerator, and then we use that to figure out where the car is going to be in the future. And then the combination of this information can then be used for planning to figure out, given my end objective, like to get to this point in the road, what actions do I need to apply to get there safely? So say you predict where the cars are going to be in the future, and then our car wants to turn to this lane. So we would use our action models to say, well, what are the steps we need to do to get there? This is a gross approximation of how self-driving cars work, but you get the general idea. So a database, I would argue, basically is the same, right? So the first is you have your perception. You're trying to understand what the application is trying to ask the database to do, what queries to execute, what data to store. And we want to be able to forecast what's going to happen in the future. Like given my query trace, given the expected arrival rate of transactions and other data, can I predict what I'm going to have to do in the future? And we can train models to figure this out for us. We're calling this workload forecasting. The next step is to actually understand the internals of the database system and how its behavior will change if we start applying actions like building an index, changing a knob in when you execute this workload in the future. So the basic idea is you can decompose a complex software system like Postgres into its individual components, like the auto vacuum, building a hash table, doing a filter on a scan operation. And then you can train models that can predict the resource consumption and elapsed time for these different components. And then you can add this together and say, well, here's the elapsed time to execute a query, or here's how much CPU, disk, and memory I'm going to use. And that can help guide you to understand how the changes you may apply will affect your objective function. And then putting this all together, now you have a way to select, here's the actions I want to apply for given my database, like here's my columns and my tables, and here's the indexes I could build, or here's the knobs I could tune. And then you use the forecast to say, this is what I need to execute. This is where I want to, my objective. I want to be able to execute these queries from now into the future. And then you have a way to then plan the actions using the behavior models that we've trained in the middle part here to say, this is the best action you want to apply to make the change, again, to keep moving forward the system. So again, gross approximation, but you get the general idea of why we're saying this is self-driving, why this is you have to sort of model, look at the internals of the system to figure this low-level information out. So now the question is, does Postgres already have what we need to achieve a fully autonomous self-driving database system? And when we first started this research at the university, we did look at Postgres in the beginning, I think 9.3, 9.4, a few years ago, and we decided that there was just sort of a bunch of limitations of what we wanted to do, at least in the beginning, and that Postgres didn't have the right APIs and the right exposure to the information that we needed. So we ended up building our own database system. And since then, we've come back around, mostly because of the pandemic, and I can't run a team at the university remotely to try to build a system. And now we're actually looking at applying the self-driving stuff we've developed before, now applying it to Postgres. And so I want to talk about, like, okay, what have we learned since then, since coming back to Postgres, and what techniques, what methods, or what things does Postgres expose to us that allow us to achieve this goal of a self-driving system. So I want to talk about four basic areas of work we've looked into and some of the challenges we faced. What exists and what do we like, and what are the things that are limiting what we can actually do. And again, the high level of how the system would work is you observe the system, watch what happens when it executes queries, you learn from that execution, you learn from the behavior of the system, and then you deploy an action, see whether it makes things better or worse, and then repeat the process, observe and learn over and over again. So again, I'm going to talk about four areas: how to do workload capture, collect the metrics that we need for training data, the what if API to predict what the query planner will do or what the system will do for a given query plan in the future, and then how to deploy actions. I would say this is also true. This is not comprehensive. There's other aspects of Postgres that we find sort of limiting or have been super helpful for us. And I can talk about offline or in Discord, but these are the sort of the major 4 things that we've been looking into. So the first issue is workload capture. So the idea is that you're running a database system in production. You need to be able to retrieve what queries they're executing, what the database looks like, so that we can be able to simulate an environment with that real workload and that real data set, run a bunch of experiments to try different configurations that we don't know whether are going to help or not, learn from that, and then deploy the actions in the production. Right? It's super important in machine learning models to avoid overfitting, that you need to see examples of both good configurations and bad configurations. Like bad configurations are super useful for us to understand, okay, maybe this is a region of the solution curve we should avoid. But of course, again, you don't want to do this in production because nobody wants their system to go down or crash or get super slow because you're trying to learn something in the very beginning. So again, the idea is that we want to then have a simulated environment that can mimic as close as possible what the production database is actually doing, so that we can learn from there safely and then apply it to the production. So with workload capture, the idea is that while the application is running real queries, we want to be able to record what queries it is actually executing, like literally the SQL strings that it's sending over the wire. And then we also need to collect a snapshot of the database, at the moment, the beginning of when we acquire the trace. And so for this, the tools we use that have been pretty useful for us is Postgres collector, obviously built in. Postgres has a built-in collector that allows you to retrieve query logs. Of course, we use pgdump to take snapshots. If you're running on RDS or Azure, there's a way, they have click button ways to do this more efficiently. We have investigated using techniques like the Postgres AI's guys database lab engine. You can do basic copy and write snapshots through ZFS. This works as well, but of course requires you to run on ZFS, which not everyone does. All right, so now you have the workload trace and the database snapshot. You can send this over to a spare machine, use pgrestore to replay the database or to load it back in. You use the workload trace to train workload forecasts and say, here's the queries I'm executing in the future. And then that basically spits out what the SQL queries literally are going to be with new input parameters. And then we use a trainer program that takes in that new future workload trace, and we just use PG replay for this, execute it on the database, collect a bunch of new training data for new actions that we haven't seen before or trying out for the first time, train new models, update the trainer to again explore spaces that we haven't seen before. So again, the key idea here is that the thing we're executing offline are actually future queries. A lot of existing work is always looking like query traces in the past and saying, okay, here's the problems I had before. How do I make sure it doesn't happen again? But if you think about how DBAs actually use databases today, they're looking for in the future, understanding like if there's a major deadline, new product releases, new features coming out, and you need to be able to prepare accordingly. So this is why we have to be able to do this offline, but also then use our forecast to say what's coming in the future. I would say there's a bunch of papers that are out now in academia about how to reuse training data from existing production databases and apply them to new database scenarios. This is basically using a method called like transfer learning or knowledge transfer, where you can learn from one database and help you make decisions on a new database. The best of my knowledge, everyone claims you can do this. Nobody has actually done this in production at scale yet. And so this is why you need this sort of offline environment to figure this out. I mean, it's super hard to do that knowledge transfer. All right, so what are the open problems that are facing in workload capture? So Postgres collector, it's okay. It's not the best way to get query traces. It'll do it, but we find it has a high overhead, especially if you have a high throughput or high submission rate of queries from your application. And there's no really fine-grained way to control what queries get logged. And so you can set a parameter, say if it's slower than this, so many milliseconds, log it. But if you're trying to get every single query, then this is difficult to do. I mean, pgstat statements can record a digest as well, but it doesn't keep track of the input parameters, which is super important to understand how the working set evolves over time. The other big challenge too, if you're doing this kind of logging, is that you're going to lose the type information for prepared statements. So it's going to cast every input parameter to prepared statement as a text. and you don't have the low-level information about the type of information that you could get from the schema. And there's been some recent work, not at Carnegie Mellon, but there's a new paper coming out in Sigma this year where they actually rely on the query trace to actually include the number of rows that are returned from Postgres. And that's not something the Postgres collector can get right now. So we think the better way to do this is actually use a proxy, have something that you can selectively watch traffic and port it without having to go through Postgres. But that's my knowledge. This doesn't exist yet. The other challenge we face is that PG replays. It's good, but again, it's not perfect. The biggest limitation is its single-threaded playback. For OLAP workloads, this doesn't matter, but for operational workloads that are highly concurrent, it's really hard to mimic exactly what the production database is experiencing in the offline simulation. And so, I realize this is a Postgres conference, but in our experience, especially with OtterTune as a startup, the best tool that does workload replay we've seen so far is Oracle, the Rapid Application Testing or Tester, the RAT. We have found this to be be able to simulate an environment offline that has the sort of right amount of concurrency and parallelism as the production database. All right, so the next thing we want to do is collect metrics. So the metrics are the runtime internal telemetry that every database system generates, Postgres generates, that keeps track of what the system actually does when it executes queries. And this is a more fine-grained information about exactly what tables got updated, how are they accessed, and so forth. So the example of this would be in Postgres, would be pgstat user tables. Like that'll tell you the number of tuples inserted, deleted, number, and so forth. So the reason why we want this data is because it's useful for not only for the behavior modeling, but other aspects of an autonomous system that you may want to be able to reuse training data maybe from a database that's close by. That's something we do in OtterTune. But also causal analysis to understand, there was a performance anomaly, what part of the system caused this problem based on these metrics, and then therefore that can influence what actions I apply to try to correct things. So the basic idea is that, again, you have your production database. We're going to collect everything that we can from that Postgres exposes. So not only are the statistics and the internal metrics that the system is generating, but also the current state of the database. So what are the current knob configurations and PG settings, what the schema looks like in PG catalog, and then what is the data distributions or the statistics that the analyze collects from the tables themselves. And then we just store this in our training repository in snapshots over time, and then we can train statistical models that can predict how things will evolve in the future, right? And again, for the most part, Postgres has a really robust and featureful metric subsystem, so we don't really, at least for the research side, we don't have any complaints about this for now. But there are some additional things that we do want to get that we think we're going to need. Postgres doesn't expose and it could cause problems. So the biggest issue is that since Postgres relies pretty heavily on the OS for a bunch of functionality, like the OS page cache and scheduling the workers, some aspects of the runtime behavior are simply just not exposed through Postgres metrics, right? So like if you have a buffer pool miss, you can keep track of that, and you can also derive what table got missed or what index page was missing. But now if you go down to the OS and do the lookup and there's a major page fault, you don't know whether, from Postgres' perspective, you don't know whether it was a minor or major page fault, right? Because the OS is hiding whether something's in the cache. So one of the ways we're actually looking to solve this problem is that my number one PhD student now is investigating how to use Linux DPF, or these kernel programs you can run down in Linux, latest version of Linux, to collect additional information about what the database system is doing, and then expose that as training data or throws as metrics outside of as Postgres. The basic idea is that there's a symbiotic relationship between some code or extension running in Postgres and the DPF program running in the kernel, and you understand what is what the database system is actually doing when it touches the OS. Another thing we may need as well, Postgres doesn't do this, at least as far as I know, but some of the commercial systems do, to run micro benchmarks when the system boots up to understand what the hardware actually can do. Like it's almost like BOGO MIPS when you boot up Linux. But it's not enough just to do this at the beginning upon system boot. You also want to do this periodically to understand if there's deviations or changes or degradations in the hardware over time. And the reason why this matters is that if we apply an action today and things are super fast, but a week from now we apply the same action and things got slower, we need to understand, is it because the database has changed, the workload has changed, or actually the hardware having problems in making things slower for us? All right, so the next one is probably the hardest one, at least in my opinion of all of these, is the what if API of the database system. So the what if API is this idea that Microsoft developed or proposed in the late 1990s of allowing the database system to generate query plans, the optimizer planner to generate query plans for SQL queries as if it had certain certain indexes installed in the database, even though it doesn't actually, right? So the idea is that if I have my SQL query like this, I want to go to my database system and run explain and get back what the query plan is going to be without actually executing it. The database system is going to look into its catalog and figure out, okay, for this table, I have these indexes, and determine whether there is a matching index that can satisfy this query. And then uses that to spit back, here's the query plan that you would execute. But when we're actually doing our investigation or experiments on the offline simulator, we want to be able to try out indexes, but actually having to build them. Because if I have a 1 petabyte table or 1 terabyte table, I can't be adding and dropping indexes over and over again to figure out which one's actually going to work. So what I want to be able to do is go to the database system and say, hey, pretend you actually have this index on these 2 columns. What would the query plan actually look like? And if the index is actually helpful, you would get a new query plan that would actually use the index. They can use that to determine whether the database system is actually going to choose the indexes you're trying to apply. Right? Same for table partitioning. Knobs are a little bit tricky. We can discuss that later. Again, the reason why you want this is because you don't want to have to build 2 separate models or build a separate model to try to predict what the query optimizer is going to do. Right? It doesn't help me by my model says, hey, this index is going to make a huge difference. You should totally build it. And then we build it, and then the optimizer says, I don't want that, and it never actually picks it. Then we just wasted a bunch of work and time building index that the system doesn't want to use. So this allows us to be able to try things out without actually having to build it. So why is this problematic in Postgres now? So from our perspective, we find the what if API functionality in Postgres is quite limited. So it's fantastic that there's an extension API that you can build these kind of things, but the only one that we found at least has been for indexes in HypoPG. For knobs, as I said, it's tricky because there are knobs that will take effect in the planner decisions, like turning off merge join or hash join and so forth, things like that. But there's other aspects there are other knobs that affect the runtime behavior of Postgres that simply the optimizer just doesn't reason about at all. It would be difficult to actually do this. So you can't get what if, you can't use what if for that. And then for partitioning, again, the best of our knowledge in looking online, we haven't seen anything equivalent to HypoPG that can handle table partitions. The other big challenge, and maybe this is like completely impossible to actually do what I'm proposing, is that especially in Postgres, that there's physical data structures or the properties of physical data structures will affect the query's performance. And these are things that the optimizer planner cannot even consider or reason about because you don't know them ahead of time. So an example would be like the table fill factor or how often you're running the vacuum, right? How long is a version change going to be when you do a tuple lookup? Right? That can affect, am I reading 100 pages, 1 page? That can have a huge difference in performance. So to the best of my knowledge, not even the commercial systems and even SQL Server can take these things into consideration. Again, the way Postgres does MVCC makes some of these problems a bit more pernicious than maybe say how MySQL does MVCC. All right, and then the last one is that there are implicit costs during query execution that Postgres explain doesn't produce or doesn't consider in its cost output. So, for example, if I have an update query, you can get the query plan cost with explain that tells you, here's how to cost of doing the index scan and the modification. But there's a bunch of other stuff Postgres is going to do implicitly because of foreign key checks, integrity checks, updating indexes that aren't included in the cost at all. So that means we have to build separate models on the outside to approximate or guess, here's what Postgres is actually going to do when I update this table. Right? Update a table that has 1 index versus the 1,000 indexes. Obviously, the 1,000 indexes one is going to be more expensive. All right, so the last issue is with the action API. So again, the idea is that there's some planning component that says, here's the indexes I want to build, here's the knobs that I want to tune, and then we have to tell Postgres to apply those changes. And so for the most part, we've been pretty satisfied what Postgres exposes to us. And it's more than just saying, build this index. There's, when should you build the index? And that's all covered by the forecasting stuff we talked about before. But there's also the question of how to apply the action. Like, how many threads or how many workers should I use when I build the index? Because if I'm running it in a production machine, maybe it's during the day and it's high traffic, maybe I only want to use one worker. But if it's nighttime when demand is lower, maybe I can use all the workers. Right? So again, for the most part, Postgres exposes everything that we need. And so the basic idea, again, we have our production database, we have our training environment, the machine learning components are trying to try out new actions to see whether they help. And then if we find one that helps, we want to apply it to production database. So there's when should I make this change? And then how should we make them? Are the two key things we have to deal with here. So my biggest complaint, and this is not specific to Postgres, is that there are a bunch of knobs that don't take effect in Postgres until you restart the database system. Mac worker processes is probably the one we would encounter the most. And the reason why this matters is that it limits the number of actions maybe you can apply to the database system and without having to restart. And then if you have a large data set or a large database, then having to restart and some changes have to do compaction and so forth, like the restart cost now starts to become larger and larger, and it limits how much new data or how much new training scenarios you can see. So this is not a deal breaker. There's ways to get around this. You can sort of use a proxy to maybe maintain 2 machines and flip sessions over to avoid, to hide the restart cost on the production database. In the case of OtterTune, what we actually do is you can specify when you are allowed to actually restart the system. So you can maybe try out some knobs, collect some training data on the knobs that don't require a restart, and then maybe once a day or twice a day within a certain time window, go ahead and do a restart. Again, this doesn't solve the problem of the cost of restarting, but it allows you to maybe focus on tuning or focus on learning about the knobs that don't require a restart, and then occasionally learn about the ones that do require a restart. It just takes longer to collect the data. The other thing that we like about Postgres is that the support for concurrent and parallel index creation is good enough for what we need. Again, being able to control exactly the number of workers that you're going to use to build an index is perfect. Best of my knowledge, there's no way to do non-blocking table partitioning, meaning I can create a partition, I take an existing table and create partitions for it efficiently without having to stop the world of take an entire lock on the table. This is hard because partitioning is probably the most expensive action that we're trying to consider because you're copying a lots of data, and we don't have a good workaround for this just yet. I mean, ideally, it would be nice to be able to, just like make a shadow table, start partitioning it, then still have updates get applied to it. Triggers might be able to do that for us, but we haven't gone that far yet. So just sort of finishing up, I guess going back to my original question, does Postgres already have what we need? Almost. It's not 100% there, but it's pretty close. And as I was saying, the biggest limitation that we face in our own research is to get a lot more metadata or a lot more information out of explain. And so that's going to be in the combination of the what if API, but as well as what are some implicit costs to query execution with some things that are in the schema that explain doesn't consider. I'll also point out too, for this work, we can't use explain and analyze because again, we're trying to predict what the queries are going to do, future queries are going to do without actually having to run them. Trying to train models to predict this. So explain, analyze produces some additional information about your hit ratio on the buffer and so forth, but that comes afterwards after you execute the query. So we're trying to avoid having to execute the query so we can accelerate the training data collection process. And so this is a bold statement. It's only 8 years away. I keep maybe thinking it's 2020, but it's not. But I think an aggressive schedule could get us to a fully self-driving Postgres by the end of the decade, by 2030. And again, what I mean by that is not having a human, requiring a human to make any changes, monitor the system, account for workload shifts and things like that. All that can be entirely automated. I think that's possible by the end of this decade. And what makes you really excited about this is once you achieve full automation, you can start using the system itself to discover new optimizations, new ways to run Postgres, to run a database system that are non-intuitive or not easily discernible by humans, right? Oops, sorry. And you see this technique used in other aspects of science and other aspects of research, right? So there's an article a few months ago in where they discuss how there's been researchers on battery technology, radiology, cancer research, and so forth, where they're using machine learning methods to help them find potential solutions that humans have not considered before. Because you can kind of just throw everything in the kitchen sink at the machine learning algorithms, and then whatever actually makes a difference, whatever can help you, pops out sort of near the top. At the gross approximation, but that's the general idea. So I think we can actually do the same thing in a database system where we can say, what are the things that a human would never ever do to the database system, but it turns out it is actually the best thing to do, right? So that I'm really excited about, and I think this is going to open up a lot of other interesting philosophical questions about autonomous software, autonomous databases that we may have to consider as well over time. If there's still a human in the loop, the human says, hey, I really want this index, but the machine learning model say, that's a stupid idea, I don't want that index. Who should win, right? Well, you may say, oh, the human's actually paying for the software, paying for the hardware, let them make that decision, but maybe we temporarily do it and just watch over time to see whether that's the right thing. Or should we have no ability remove any ability for a human to touch it? Again, it's interesting discussion. I don't know the answer. Okay, so I'm finishing up here, but if there's some additional information about the kind of stuff we're doing, so the 3 areas you can look at are, again, the commercial version of some of the auto-tuning stuff we were doing with Postgres, now called OtterTune, that's been spun off. The NoisePage project is the university research on the self-driving version of Postgres that I mentioned here today. And then I'm teaching a course this semester specifically on self-driving database systems. And you can check the link out and see a bunch of the papers that students and I have been presenting and discussing. So with that, I'm finished up. Happy to answer any questions. Thanks.
All right, thank you so much, Andy. That was super interesting. I think we're on a tight schedule, so we're going to continue with the next talk. But thank you so much. This was fascinating.